Raul Leal Rodriguez from Amsterdam.
Do I have 4 minutes or do I have 10?
You have 20 minutes.
Okay, as it was said by Maya and Hela, I'm not sure how this will be related. My first intention was to come here to understand this quantum people does, because they use a lot of words that are similar to the words that I use. I was looking for an interesting example, but then the organizers kindly helped me passing the British migration, and then very smartly, then they asked me for a talk, and then I feel morally obliged to give the talk, and then I could not say no. So I'm going to try to keep it short.
I thought you were thank us for giving you the opportunity.
That's what I say. I try to reply politically correct. So I'm going to talk about modalities in the Stone Age. Before I start, I want to know some publicity that the 91st Peripatetic Seminar on Chips and Logic goes Dutch. Namely, that is going to be the last weekend in November in Amsterdam. And I see that nobody from Oxford is there yet. There's Cambridge people there.
Means we get only cameramen and stuff like that. Yes.
So this is just publicity. Now, I want to talk about the Stone Age. I want to apply the Stone Age. So what I'm going to try to do is I'm going to try to keep this talk simple and tell you what this coalgebraic logic people does. So what does this people do? Well, they have a coalgebra functor, which they say that is a one-step transition system where a state has some kind of transition to some other technical state. And what they do is they try to do something that they call coalgebraic logic, which is usually they have a category of algebras and they put operators over this category of algebras, and they say these are modal operators. Usually it's done over Boolean algebras, and then they say we can relate those things via stone duality, and then, well, yeah, this is not actually stone duality, it's an adjunction coming from stone duality. They relate those things, and they say we can do modal logic. And now my claim is that essentially what we have been doing a lot of modal logic is based in this stone perspective, and that's what I want to talk. So there comes the definition. The formal definition is that then a coalgebraic modal logic for T is a functor L together with the natural transformation LP to PT, plus some extra assumptions on L, but to keep it light, I'm not going to say what they are. But there are some assumptions there. And what I'm going to do in this talk is just explain this definition. That's all that I'm going to do in this talk. I'm going to explain you how to produce functors from concrete modalities, and I'm trying to explain you how to produce modalities from functors. This is all that I intend to do in this talk. So let's see. Let's try to use logic to describe quadrants. The point is that the logic is going to be given by the initial algebra of L. So if you have a category of Boolean algebras and then you put a functor over the category of Boolean algebras, then you are adding operators. So you can think of Boolean algebras as operators. So the logic is going to be given by the initial algebra. We will use this natural transformation delta to transform coalgebras into algebras. And then we will use the semantics given by initiality. Let's repeat that again because that's important. So this is the diagram that you have today. So what I say is coalgebraic logic gives you logic by an initial algebra. So think of that as a term algebra plus some operations. Now you use delta to transform something that you say, oh, okay, this was weird, and then this is a coalgebra, and then I use delta, and then I switch this into an L algebra over P of X. Yeah? And this is the complex algebra. And then, by magic, then you get the semantics by initiality. Just the initial map from the initial algebra to this complex algebra. And that's how things work. So let's try to do one example. Basic modal logic with the box modality that says S satisfies box of 5 if all the successors of S satisfy those things. So you want to get somehow, you want to get a functor L over the category of Boolean algebras, and you want to get a natural transformation. So it is well known that basic modal logic relates to coalgebras for the covariant powers. And now what you do for the logic is essentially something that, what you do is you take an algebra, a Boolean algebra, and then you put a box in front of all the elements of the Boolean algebra, and then you generate another Boolean algebra. What you do here is you forget that you got a Boolean algebra, you put one operation, and then you generate it. So if you replace that thing, this is what you want. You want a natural transformation from F to PX. So you take a power set You forget that there was a Boolean algebra and then you generate. This is putting one modality on top. So you want that. And now you have a left adjoint on the left. So when you have a left adjoint on the left, you just move it to the right. Yeah?
Don't want to assume any axioms for this.
Not yet. No? I'm just trying to tell you how to produce the modalities. Yeah? Now you move it to the right and now it becomes UPX to UPTX. And then you realize this, that is that. If you take the contravariant power sets functor to Boolean algebras and then you forget that it was a Boolean algebra, you get the contravariant power set functor now in the category of sets. And now the things becomes another transformation from here to here. And now you can define it just using what you want. So let's read this thing. So it was what it was before in the case that we added one modality. So we have the box and we want to see how this diagram works. So you take an element here, which is a formula, you apply a box, so you get box of I and then you move, so you're moving by this direction. So you want to see what is the semantics of this guy. So by the diagram, what you just write what the diagram tells you, and this is, you apply the definition, and then computing all those things, you get that the semantic of box using this natural transformation are all the states such that all their successors are a subset of 5. This is exactly what the box does. No? This is this coalgebraic thing is actually making sense and it's really capturing the example that we want to capture. So then you can say, hey, modal logic has two modalities. Well, one answer is, well, you can define the diamond in terms of the box. But as Sam and Mike told us, well, this is not really what you might want, because perhaps you don't want to use negation, so you don't want it. So you should better use two predicate liftings. You should better use, now put two different boxes, so for each box you generate, or for each modality you generate. And in general, what you're going to do is take factor of those modalities, and then you come to the definition that there was mentioned, and this is the definition of predicate lifting, and this is what a concrete modality is. So if you just transform, and this really tells you what a modality should do. A modality is something that takes properties of a state and transforms it into properties of their successors. And that's what those predicate liftings do. And that's what they do. If you want to know how to obtain the diamond, then you get it. Let's try to do another example. Probabilistic model. So probabilistic model logic has this idea that for each rational number, you have a modality that says the probability that this is the case is larger than p. So you want to get that. So since you will have many, and I was studying that you will have to take products of three algebras over the rational numbers, because each rational number is going to give you modality. And then those coalgebras are giving you, but what Bart was telling you, the distribution factor. This can be with finite support. So all the they're supposed to be equal, but okay, you can also do it for less than 1. This is the subprobability distribution factor. And then you can use this factor. And then the probability, the usual probabilistic modalities, and then obtain. You just take the x of A, you assume that this is a set, and then you just send it to all the probability distributions that assign to this set a probability larger than p. And this is what a probabilistic modality does, and that's how you obtain it. What about if you need many arguments into modalities? Well, if you need many arguments, what you do is you just take the free algebra of the product of the Boolean algebras, which is natural transformation from Qn to Q of t. And in general, the logic is given by a coproduct of those guys. Now, how to incorporate actions? Essentially what you do is you take a quotient of this functor, which I'm not going to explain here because this can be very technical, and then you use co-equalizer properties to mambo jumbo. And everything at the end is going to be about those predicate liftings, about how those predicate liftings are satisfying the equations, and then you can extend this to everything. What is important to know that is that this approach only allows you to work on round 1 actions. So I can say things like this. Box A and B, for instance, that the box preserves conjunctions, but I cannot say things like box diamond A is equal to diamond A, because this is not a rank 1 formula. So I can only use one layer of modality. This is a shortcoming at some point of this approach, that you can only talk about the one-step behavior of what's happening in the next state of the system. Yeah? So there's some duality. So that was the original picture. And that was what we had. But if we analyze what we really need to understand, to interpret those modalities, we really need a much basic structure. What we really need is some algebras for the base category. So that's how my Sam was telling us. You just take a variety of algebras, which can be something different, like distributive lattices, because perhaps you don't want to use negation. Yeah? And then what you need is, I'm keeping the simpler picture. This gets a bit weird sometimes, because, and then I just say the whole Travail powers a functor into the variety of algebras. And then what you need is that this diagram is commutative. So it's that this guy, but the point here is that sets are nuts. But the importance of sets there is that there is state space. So this is the space of a, how do you say that? The Argyll states. So a set is the type of a space. But you could in principle use a much interesting structure, which usually happens. If you want to put less structure on the category of algebras, you have to put more structure in the category of sets. But as Barr told us, well, there are locations you really don't need to go out of sets, and I do not understand that. So I keep it just on sets. Yeah? So this thing becomes really this thing. And what is important here is that P, I don't use P because of powers, I use P because of properties. And the intuition of this P, the P, is that you transform your state space and you send some type of properties, P for property. Yeah? And you want those things to be in some category of algebras because you want to do some algebra with your properties, because that's what properties are for. Yeah? And now you need to forget and need to do something with this Q. I will come back to that later, because the use of the contravariant powers of functor here is that it's a home functor. Yeah? So what you really need behind this intuition is some schizophrenic adjunction, which is essentially set up. You know the ultrafilter functor of A is also equal to Boolean algebras of A to the 2. So this is also representable functor. That's what is called a schizophrenic adjunction. And the point is that we need, for this framework, I need Q because somehow I need to classify the states. But I don't need a topos. And that's something that is strange, and I do not really understand here. If you have a topos, I mean, if you are concrete over a topos, things should work because you have a subobject classifier there. But you could also, as you do in sets, you could very well move to some other things and get some other type of classifiers. Another question is how, assume that you are walking on the wild and then you find a quality. So for instance, you come to Amsterdam and then you find Mosel, which is a logic for each one. And then you see that, and then you see that it has nice properties. For instance, I'm not going to explain you this, but this is a logic that appeared first in automata theory and for non-well-founded set theory, and in Amsterdam they call it concrete, that's why I say concrete between them. Another question is how can you obtain an actual concrete operation from a random functor? So how do you extract operations from functors? How do you extract operations from a set functor, or how do you extract algebraic operations from a functor in a finite variety? And what you do there is you present the functors, which is essentially a Juneda lemma. So if you want to do it in sets, you take a signature where for each t of k, for each p, you finite an operation and then you define those things. They are the traditional Juneda lemma. And this is a polynomial functor, so it can be understood as the signature of some operation. Yeah? So you can think of t as being presented by some algebraic signature. And the question is, how do you do that in the other set? How do you do it if you're in a random algebraic category? Well, if you're in a random algebraic category, well, it doesn't have to be so random, it has to be finite, because otherwise things don't work nicely. Was you use free algebras. But one of the properties of those nice finitary categories is that you only have to understand 3 algebras over finitely presentable objects, and then you do the same trick. So you start with an element from a function. You can think that as an evaluation function into some algebra. You move the right adjoint to the left, and then it becomes left, and then you just apply the functor, and then you just do this. And this is what you know. And this is essentially during a presentation. What we will be used here is another lemma that says every element in UL of K gives you a natural transformation from UK to U of L. And how do you do that? Well, I mean, assume that you have a coalgebraic logic, and assume that you have those operations. And you can pre-compose with the presentation, and then magic. A concrete modality has appeared. Remember this diagram. So this thing above becomes this thing below. So using this presentation of functors, you get your concrete operations. So, and this is a technical reason why I really like to use Q, because Q is representable, and then I can use Uneda lemma to produce the concrete modalities. In principle, perhaps there is another way to go around that, but I don't know it yet. I will ignore this because this is a bit technical. I mean, essentially, it's how do you decompose this Naula modality for the distribution factor. What is important to know here is that using this technology of presentations, you can restrict things to finite arities, and then you can just bound how you are making your searches. And the probabilistic modalities come like that. An application is that if, for instance, if this random logic that you found on the Y has an axiomatization like this, that has some terms and you do some crazy things there, and then you apply some T's, some operators. If you do this coalgebra, you have this axiomatization, and you can do this technology, and this becomes this. So you can transform those multi-sorted equational logic, multi-sorted modal logics, you just transform that into equational logics, the ones that we like and love. And we can do those things. So to finish, where I have just shown you the basic picture of how to produce modalities using a strong duality, and perhaps something that is interesting is to investigate this framework when you move out of sets. So this is all that I wanted to say.
Thank you very much. Questions?
So on the syntactical side, you said that we can do this for essentially any variety that is sort of denoted by sort of A.
This will be finitary.
Yeah. Okay. So what happens if you take A to be sort of hating algebras? Have you played around with any varieties? So what happens if you sort of change the base?
This is a very good question, and this is an example that I have been trying to see what happens. I haven't worked it out, but in principle it should work. The problem will be to find the predicate lifting. And what doesn't work nicely is that I don't really want to use the contravariant powers of functor because I have S-stress structure. But if what you want is just to define a modality on hating algebras, you can just do it using that every Boolean algebra is a hating algebra. But if you want to use more, you need the ultrafilter factor, and then you would like to change Q.
Yep.
But I haven't worked on that. This is a very interesting question that I would like to see.
No?
Jag är först med en annan ansvar.